How do you see the unseeable? How do you explore the inescapable? Our cleverest astronomers have figured out ways to catch light that skims the very edge of black holes. Let's find out what they learned. A few weeks ago, a story made the rounds of pop-sci media proclaiming for the first time that light had been detected from behind a black hole. The reports were about a paper that claimed to have seen X-rays that came not from inside a black hole, but from the backside of a black hole. Now, this is obviously cool stuff. I mean, really, anything new with black holes captures the public attention. But this result is cool in ways that most people aren't aware, and it brought us closer to a goal that I have been personally striving for years. Trying to understand what happens in the vicinity of the largest black holes in the universe. Now, you might remember the picture of the black hole captured by the Event Horizon Telescope. We talked about this soon after it came out, but to remind you, here we have radio light from charged particles whirling around the black hole, and the more recent version of this in polarized light shows the grain of the magnetic field right near the black hole's edge. This image was produced through a Herculean effort, a team of hundreds of scientists and engineers synthesizing data from radio telescopes across the globe. They stitched the image together using the very latest machine learning techniques to achieve an image resolution equivalent to a telescope the size of the planet Earth. All very impressive, very state-of-the-art. But the thing I love about the result we're discussing today is its simple elegance. We've been using the same technique for decades to understand quasars. This method doesn't need an international team or a planet-sized telescope. It can be done with a single ordinary scope and one astronomer with lots of patience. The technique is reverberation mapping, in which we watch as a flare of light from a violent event near a black hole radiates and reverberates its way through the complex structure of a quasar. When that light reaches us, many millions of light years away, it's still imprinted with a wealth of information about the monster that it escaped. Reverberation mapping is all about untangling that information. We do this by watching how the spectrum of the quasar changes over the time. A spectrum, by the way, is what you get when you split light into its component colors or wavelengths. So basically, you watch the quasar, which is just a faint point of light on the sky, and stretch it into an even fainter flickering rainbow, and then try to pull from that the full 3D map of the quasar. To understand exactly how astrophysicists do this, I'm going to take you on a journey. We're going to follow a flare from its origin deep in the belly of the beast, uncomfortably close to the supermassive black hole. Supermassive, by the way, is the actual technical term for the largest black holes in the universe, anything more than 1 million or so times the mass of the Sun. These things are pretty much only found in the very centers of galaxies, and pretty much every decent-sized galaxy has one of these at their center. They are mostly dark, except when a bunch of gas shows up in the galactic core. Then you get this gigantic whirlpool of searing plasma screaming around the black hole, aka an accretion disk, and switching on the quasar. Quasars are not what you'd call stable. They sputter and flare with violent events, for example as dense clumps of gas hit the center, or magnetic instabilities shake things up. However it happens, when a flare is generated near the black hole, it expands outwards, and it causes a lot of trouble along the way. The expanding shell first rips across the surface of the accretion disk, causing different parts of the disk to brighten. First the shorter wavelength, which corresponds to the hot inner disk, then to longer wavelengths of the cooler outer regions. The flare then continues outwards and upwards. Although it's energetic, the accretion disk is relatively well behaved, at least compared to the wild stuff all around it. A maelstrom of lower density gas rages above and below and beyond the accretion disk. That gas is accelerated by a combination of the incredible gravitational field of the black hole and the continuous blaze of high-energy radiation from the inner accretion disk. It can be driven to up to 10% or more of the speed of light. Pockets of gas within this flow are somehow shielded, and so that gas can cool down a bit. This gas starts to glow in a different way, not from heat, but from the motion of electrons between their atomic energy levels. This allows the maelstrom to reprocess some of the light of the accretion disk so that it shines bright in very specific colors depending on what atoms are present. In a normal spectrum, we see light from these electron transitions as sharp spikes at specific wavelengths, what we call emission lines. But in a quasar, the gas is moving fast, and that motion shifts the wavelengths of light as we see it. Now, we've all experienced this Doppler shift when the sound waves of an ambulance siren shift between higher and lower pitch as it passes us on the street. In the case of the quasar's emission lines, gas is moving towards us and away from us at many different speeds. The sharp emission lines get shifted to many different degrees and add together to produce the classic broad emission lines, perhaps the most striking feature of the quasar spectrum, and one that confused the hell out of astronomers who first saw them. And honestly, it's been confusing us ever since. From the Doppler shift, we can tell that the gas is moving fast, but that doesn't tell us what drives the gas. Is this stuff that's pouring towards the black hole, or orbiting it, or being blasted out by the crazy radiation from the accretion disk? Now, this is where reverberation mapping can be the most powerful. The light from this gas is ultimately powered by the light from the accretion disk. So when our expanding shell of light rips through this gas, the broad lines get supercharged, but in a complicated way. First the gas near the centre brightens, then the gas further out. At the same time, the response of the gas on the far side of the quasar is slower than the gas on the near side because the far side's light has to travel further to get to us. Let's look at a simplistic example. Two totally different scenarios for how gas might be moving. One, it's pouring in, rivers of gas dragged down by the black hole's gravity. And two, it's being blasted out, riding the flow of radiation from the inner accretion disk. Either of these scenarios could produce the same Doppler broadened emission lines, but reverberation mapping can tell between them. Consider case 1. If gas is pouring in, then it's accelerating, moving fastest towards the centre. This means this extreme velocity gas, the far ends of the broad line, should respond first as our flare reverberates out. Also in this scenario, the gas on the far side of the black hole is moving towards the black hole and so towards us. Its light is blue shifted to shorter wavelengths. That gas responds late to the flare because the light has to take this roundabout journey. Meanwhile, the gas closer to us is actually moving away from us as it falls towards the black hole. It's red shifted to longer wavelengths and it responds before the blue shifted light. So in the inflow model, the quickest response is for the red side of the emission line, the slowest for the blue side. It's exactly the opposite for case 2. If gas is being blasted out, then the gas accelerates outwards, so we expect the faster moving gas to respond later than the slow gas. And now the gas on the far side of the black hole is moving away, while the gas on our side is moving towards us. So the red shifted gas responds after the blue shifted gas. Oh, and I forgot the third option. Maybe the gas is swirling around in a giant tornado above the accretion disk. In that case, inner gas is moving faster, like in the infall case, but now the red and blue sides should respond at roughly the same time. Reverberation mapping has helped us tell between these three scenarios. Well, sort of anyway. It turns out that all three types of motion are seen in different quasars. The emerging picture is that gas falls in along some trajectories but then gets lifted up from the accretion disk by the blazing radiation of the inner disk into a vortex, and then it's blasted outwards. That's about as far as we've got with the broadline tornado. It's really hard to do this stuff because it takes years for big powerful quasars to finish responding to a flare in the core. Over the next decades, things will get better as new telescopes like the Vera Rubin Observatory come online. We'll be able to watch millions of quasars do their thing all at the same time. Okay, it's time we got back to the discovery that started our little journey, the light that was detected from behind a black hole. The events described in the paper happened extremely close to a relatively nearby supermassive black hole. The object is I Zwicky 1, a so-called Seyfert galaxy, which is like a mini quasar, this one around 100 million light years away. Near the black hole, there are sources of light that I haven't mentioned yet. The intense radiation in this region strips almost all atoms of their electrons. That leads to a haze of high-energy electrons surrounding the black hole. As light from the accretion disk passes through this haze, it gains energy from the electrons, boosting it all the way up to X-ray energies. This is the X-ray corona. We also have winds of matter flowing at incredible speeds, but this close to the black hole, only the heaviest elements like iron can hold on to any of their electrons. We see that iron because it shines at very specific X-ray wavelengths. This is the iron K alpha line. So, here's what happened. The X-ray corona flared bright, probably in a small region right above the black hole. That light then spread in all directions, some travelling straight towards us, some reflected off the disk in our direction, but some also reflected off the disk on the opposite side of the black hole. And a portion of that light was then grabbed by the black hole's gravitational field and slung right back around towards us, and magnified in the process. It was, as we say, gravitationally lensed. These three paths were apparent in the three distinct phases of the flare. They were also able to see that there was a difference in the response of the different parts of the iron line. The blue side varied before the red side, and we talked about how this suggests an outflow. We have other reasons to think that this iron-laced wind also has a very powerful rotational component, so it looks like we're seeing an expanding vortex of stuff that just narrowly escaped being sucked into the black hole. The paper goes into a lot more detail than this, lots of good stuff like measuring the mass of the black hole, 30 million suns, to verifying Einstein's general theory of relativity. So you can check out the links in the description for more details. After decades of practice and inventing better and better telescopes, we are starting to get good at this game. I just love it when we can map the space around black holes by watching flickering points of light on the sky, and in that flickering reconstruct how light reverberates around the most extreme regions of space-time.